All right, so I just mentioned that linear indexing and row column indexing is important. You need to be able to index a matrix using both ways and be able to combine matrices by either concatenating them in a vector. So this will generate new columns. If you have semicolons in between, then you would combine them along the rows. Okay. RepMat is an important basic function, and reshape is another one. When you have a reshape function, what it does is it takes the first argument, which is going to be a matrix, and then you convert that matrix into a new matrix with a certain number of rows and columns. So always take your original matrix and consider it as a linear column vector. Okay, so one long vector. If you are given a matrix, you can still convert it to one long column vector using the ordering that MATLAB uses. You get the first column and then the second column and so on. Okay, and then you look at R. That's how many rows you will get as a result. And then you start from the top. You generate that many rows. Let's say R is 5. Then you take the next 5 and put it over here. Next 5, put it over here. Okay? And so on. All right? So if you have your original matrix, the number of elements in original matrix will give you constraints on the combinations of R and C you can use. So if your original matrix has 12 elements, let's say it's a 1 by 12 matrix, then R can be 3, 4, 4, R and C can be 3, 4, 4, 3, 12, 1, 6, 2, and so on. Okay, but always their multiplication should be 12. Reshape does not change the number of elements in your matrix. It just changes the number of rows and columns. Since their multiplication is known, you can enter one of them and leave the other one empty, and MATLAB will calculate it for you. So instead of saying 3, 4, I can say 3 and an empty matrix. I don't bother dividing 12 by 3 and writing 4 there, so MATLAB will do it for me. So you can omit one of the two R and C variables and write down an empty vector instead. Okay? All right. In one of the recorded lectures, and also in the first lecture we had, I described how to convert binary numbers to decimals and also to hexadecimal numbers. Binary number has the base 2. Hexadecimal number has base 16. So each digit in binary number is worth powers of 2's. The first digit on the very right would be worth 2 to the power 0. The second digit would be worth 2 to the power 1, 2 to the power 2, 8, 16, and so on. And then you just multiply the digit with how much it's worth and add these up. Okay? You do the same operation regardless of what base you have. So when in base 16, the first element, the first digit is worth 16 to the power 0, 16 to the power 1, 16 to the power 2. You take each digit, multiply it with how much it's worth. So 0 times 16 to the power 0 is 0, 0 times 16 is 0, 1 times 16 to the power 2 is 256. Okay? So you multiply digits with how much they are worth, and then you add them up. That gives you the decimal number. All right? Going the other way, you always have to consider how many powers of your base you have in your original decimal number. Okay? So if you have number 35 and you are trying to write this number in base 3, you look at number 35, let me write it over here, and you consider the largest power of 3 that's contained in 35. the largest power of 3 is 27 within 35. And then how many of them do you have? Just one of them, right? So you write down 27, subtract it. So you've taken care of 27. Now you have to take care of the remaining 8. The largest power of 3 in 8 is 6. Well, the largest power is 3, but you have 2 of them. So you get 6. And you subtract that. You get the remainder 2 that you still need to take care of. The largest power of 3 within 2 is 3 to the power 0. That's 1. How many of them do you have? 2 of them. You get 0. And then you look at these numbers that were contained in your large number. This is 3 to the power 3, 3 to the power 1, 3 to the power 0. I had 1 of these. I had 2 of these. I had 2 of these. Okay? And then you start from the smallest one. That's going to go in here, 3 to the power 0. I have 2 of them. 3 to the power 1. I have 2 of them. 3 to the power 2. I don't have any. And then 3 to the power 3. I have 1 of them. Okay? And then the rest will be 0, the other digits. So this number gives you 35 in base 3. Okay? So it's very similar to what we did with converting number of days to, converting number of seconds to number of days and so on, or converting a certain number of cents to nickels, dimes, and quarters and so on, okay? In those cases, the amount that each digit was worth was not regular. So in the dollar example, we had the first one was worth 1 cent. The next digit, in a way, was worth 5 cents. Next one up 10 cents. And next unit was worth 25 cents. And next one was worth 100 cents. Okay? So there's still, it's still the same problem, right? But how much each digit is worth is not regular here, but there are powers of the base. But even in the dollar application, you would take your number of cents and you would see how many 100 cents you have in it and find that right in this box. Take care of how many cents you have left over and figure out how many quarters you have in there. And do that until you've taken care of all the cents. Okay? All right. Okay, the variable scope refers to what each function space can see in terms of variables. When you have a name in a function, it's a box that only that function can see. You can have the same names in different functions. They do not refer to the same box. Each function, you can imagine them having their own separate rooms and their own separate boxes with labels on them. And functions don't really care what other functions label their boxes with. All they care is the transaction that goes on at the door where you hand in some variables, hand in some values, and get back some other values. And even then, the names of the variables, variables that are being exchanged do not matter. You only care about what's in them. Okay? There are some qualifiers, some ways to bypass this rule. One of them was using the global qualifier. So what this does, if you say global x, it declares x as a global variable. So x will be a label that everybody who wants to see can see it. But the workspaces or the rooms that want to access this global x should also define global x. So if I have function a that says it wants to use a global variable x, and then imagine a link being formed with a global variable, and whenever you use x here, it will refer to this global variable. In function y, so in function b, again, if you say global x, and from then on, whenever you say x, it will refer to the same global variable. If you have another function c that does not say global x, but just start using x equals, let's say, 5, then this x will refer to its own private variable. Okay? Question?
Yeah. How do you establish that x first though? You just do global x in one function.
Yes, that establishes. So the first time somebody says global x, a global variable x is created, and it's actually also initialized to be an empty matrix. Okay. So to check whether somebody has stored anything in x or not, you would usually say global x, and then say if is empty x, then let's say it's going to be x equals 0. Okay. So let's say we want to write two functions a and b that want to keep track of how many times they've been called together. Okay. So anytime you call a, you want to increment x, and anytime you call b, you also want to increment x. The first time any of them is called, x will be empty, so you need to check when it's empty, you set it to 0, and then you would say x equals x plus 1, you just increment it. Next time a is called, if is empty x will not be true, it will be false, so you would be skipping this if statement and just increment x again. And you would have the same block of code in function b also. So they will be incrementing between the two of them this global variable x. Okay? All right. There's another sort of bypass to the general variable usage. Whenever you define a variable in a function, it's a new variable, it's a new box, it can start from empty. But sometimes it's desirable to sort of store the old values of the variable in your function. Using a global variable is one way of doing it, but it's sort of a dirty way of doing it because you don't really want to clutter up the global workspace. Other functions may use the same name, and you don't have as much control over what other people name their variables. Okay. So instead of that, if there's a variable that you want to keep track of only within a certain function, you would define that variable as persistent. So if I say persistent x in a function, what that does is it creates a box x. Initially it'll be empty, but every time you call that function, that variable will be there. All right? It's not going to be reinitialized. The first time that you use this x, you would again want to check if it's empty. If is empty, and let's say you put 0 in it, x equals 0, and then let's increment x again. The first time you call this function, you declare x to be persistent. So you tell MATLAB to keep that variable even after exiting that function because you intend to use it next time the function is called. And then x is empty, you put 0 in it, you increment it, it becomes 1. Later on, you call this function again. You declare it persistent, so it refers to the same box. Now it's no longer empty because its size is 1. It has a single element, it's not empty. So this if statement is skipped. You increment x again, it becomes 2. All right? Okay. So this question tests to make sure that you understand that the variables in the command workspace and the function workspace, even though they may have the same name, they are different variables. One way of preventing confusion when you are solving a problem like this is to look at a variable named x in one of the functions and consistently replace all the occurrences of x with a different name. Let's call it a. So you will replace all of these x's with a. But you have to be consistent, okay? All right? And let's do this for the next function, b. And let's do the same thing for y. I'll replace it with a c here. I'll replace it with a d here. Okay? And then you would continue solving this problem with the new variable names. So there's a function, apple x. You find its value. You cross it out. You replace it with what value was returned from this function. Function orange. You evaluate it. You remove it with whatever value. You replace it with whatever value the orange function gives you and store it in x. Okay? All right. Almost all of your homework problems ask you to write a single function. But if you've written a function, you can use it you can use it from your other functions also. Okay? So here I have two functions, apple and orange. Apple calls orange from itself, from within apple. Okay? The concept is still the same. You look at the expression, you replace it with whatever value you get from orange x. And then you multiply it with 2, you store it in x. When you have a complex expression, always look at the smallest chunk you can evaluate, calculate it, erase the original expression and replace it with what value you have in it, you have calculated. All right? Okay, the next problem is asking you to convert a linear indexing to row-column indexing. There are formulas for this. You can memorize them if you want. But you can also always sort of draw a table, an imaginary table, and try to calculate the number of rows and number of columns from it. And it's easier to look at the last value in each column when you are trying to find something like that. Okay? And again, in MATLAB, linear indexing would be using the first column, and then indexing continues from the second column, third column, and so on. Okay? So we had some examples of this in class. You can go back to them and see how they are solved. Okay, so this vectorizing code refers to taking a for loop and writing the same logic, the same type of, the same functionality without using for loops. And we had some examples of this in today's exercises. There are several things you need to be careful with. One of them is to make sure that you are using element-wise operations. Don't use a multiplication sign when you don't want to do matrix multiplication. Okay. And you would use a single AND, which is the element-wise ending, instead of double AND. So in a problem like this, you would look at, you would focus on the loop variable, the variable I. So that's the variable that you are trying to eliminate. Okay. And then you would look at the expressions. Here I have an if statement, right? To vectorize this code, I need to construct a logical vector that will do the same job as the if statement. So you need to create a logical vector that will contain true whenever this if statement is executed, meaning whenever this expression is true, and false otherwise. All right? And then that logical vector I will help you refer to the elements that you need to alter or that you need to access in this for loop with the loop variable I. So whenever you have this if, the condition being true, it will be an element here where you have a true in it. Okay, so this is I referring to an element in the logical vector having true. After you construct this capital I, you can index a matrix, and it will pick out all the elements that have true in them. And in a way, you are performing this operation right here on all the elements that you need to perform that operation on. Okay? Make sense? Yes or no? Yes? Nods? No's? The tilde symbol, or the squiggly, or whatever you call it. So that is the else part. That's you negate the logical expression. Now instead of looking all the truths, you want to look at all the falses, right? The opposites. So when you negate it, all the truths become false, all the falses become true. Let me give an example of this same problem. Edit, vectorize example. All right, so let's have a for loop that will look at all the elements of M, and if a certain condition is met, let's say the ith element is divisible by 2, okay, and the ith element is divisible by 3. You can actually mathematically combine these two and say they are divisible by 6, but let's not do that. Okay? Then let's multiply those elements with 5. Otherwise, we'll multiply them with 7. All right, so I have my matrix M, and then when you do a for loop on the number of elements and use linear indexing, you actually don't care about how this matrix is laid out. You are only considering linear indexing. So as far as this indexing is concerned, the matrix can have 3 rows, 4 columns, 4 rows, 3 columns, or 12 rows, 1 column. It doesn't really matter. It'll work exactly the same way. It'll consider the matrix as a single large column vector. Okay. So this rand I says, give me random numbers between 1 and 100. I want 3 rows and 4 columns of them. So you get 12 elements that are random numbers between 1 and 100. All right, and then you look at each one of those elements. If it is divisible by 2 and if it is divisible by 3, you multiply it by 5. So now the for loop looks at each element individually, and the variable I helps you refer to them individually one by one, and you step through the for loop where I changes at each iteration. Okay? All right. Let me make M a vector so you guys aren't, so we don't have to worry about the matrix vector difference. 1 by 1. All right, so let's try to solve this rewrite this function using linear indexing and logical indexing. Sorry, using vectorizing code, where we will use logical indexing. So we have the matrix M. What we want to do is we want to identify the items that satisfy this condition, okay? So we want to create a logical vector I where we will have a true for entries of M if they are divisible by 2 and divisible by 3. All right, so let's say these two are satisfying and the other ones are not, so they will be false. You can write a for loop to calculate I, or you can just say mod M comma 2. When you say that, the mod function will give you a vector that has the same size as input M, and it will contain the remainder of that element, each element divided by 2. Okay? So mod M comma 2 will give you a vector where you are going to have 0 or 1 because dividing with 2 will give you 0 or 1. So here you will have a 1, 0, 1, 0. And then in the next expression we'll write is, say, mod capital M divided by 3. You will again get, let's say, 1, 1, 1, 0. All right, so you'll have a 1 wherever M is divisible by 3. Sorry, I should also say equal 0 because I'm testing whether it's divisible. Okay. So you'll get a logical vector where it is true whenever this expression is satisfied and false otherwise. If you only look at the mod M3, you will get a numerical vector that will contain 0, 1, or 2. Okay, so we are only interested in divisibility, so we check the equality with 0. And then I would be ending these two vectors because I am looking for a logical vector where both conditions are satisfied. Okay, so it will go through them and end each element and give you a new vector I, which is this vector right here. That's the result of ending each of those elements. Okay, so let's do it in here. Rand I 100. I'll do 3 by 4 because it looks nicer on the screen. And then mod M divided by 2 gives you that. Okay, mod M divided by 3 gives you that. Mod M divided by 2 equal 0 will give you the items that are divisible by 2. Let me repeat mod M mod M3. And if you check mod M3 equal 0, there's only one element where it's equal to 0. So now you'll get a matrix that contains a true for that position and false elsewhere. Okay? So now I construct a logical vector using the single AND operator. And I want both of those conditions to be satisfied. And there's only one location where both of them are satisfied. Okay? I have a logical vector now, or a matrix. I can use it to index a matrix that has the same size. If I say Mi, I would be referring to the elements of I, so the elements of M, such that when you overlay I on top of M, you would be referring to the locations where I has a true in it. So that's only this element right here. So you get 96. Let me repeat M and I. So you take I, put it on top of M. You are only referring to these elements. Okay. So now we are able to access all the elements of M that satisfy this condition, right? Instead of doing them, instead of performing an operation on them one by one, you can perform that operation on all of them at once. So mi times 5 will take those elements and multiply them by 5. And then you can store the result back in back in those locations, same locations. All right? So let's do that. So 96 was multiplied by 5, and the result was stored back in the same location. Now you want to perform an operation on all the other locations when this if statement, if that statement is not true. So we want to handle this else part. So how can I refer to all the other locations? I can take I and negate it. Okay, so that will give me a new matrix where I have ones and zeros, ones whenever I had a 0, and 0 whenever I had a 1. Okay, so not I gives me that. M not I will give you the elements where, again, you have ones here. So it'll be 11 entries. You can't really fit them in a single, in the same size matrix anymore, so you'll always get a vector. So 96 is removed and all the other elements are returned. And then you multiply that with 7. And then you store the result back in the same locations. Okay? All right, makes sense? So you would take this. So this expression is the central part. You will remove the loop variable I because you no longer need it. And you will look at your operations and make sure that they are all element-wise operations. And then the if part will be like that. Instead of the loop variable, now I will have a logical vector because I'm referring to them all at once. And this will be not I. Okay? Now, as an exercise, consider this problem. Now let's make it a little bit more complicated. Else if, let's say mi, let's consider the elements where mi is a square, is an square of an integer. Square root of mi is an integer. So okay, and otherwise, let's do this. Mi times 9. So now you have to construct two separate logical vectors. All right. So there are 3 different sets of items you need to refer to, and you need to make sure that the second set considers the negation of the first set. Okay. So you would only be looking at the square numbers only when they are not divisible by 6. All right. So to solve this problem, the one way of doing it is to construct a logical vector I for the first part, like I did, and then a logical vector j, where this is true and I is false, and the last part will be I is false and j is false. Okay. So the for loop version is here. You can test it on a few examples and vectorize it, and make sure that your vectorized code gets the same answer. All right? So that's left as an exercise for you. Any questions? All right, nested loops, you need to make sure that you don't exit out of the outer loop when only the inner loop is done. So A will have values 0 to 5, and B will take values for each value of A. You will iterate B 10 to 20. And then this problem is also testing for this interesting indexing that you have here. So you are referring to the rows of X in reverse order, okay? You are adding one more column, you are adding two more columns. So you are referring to rows of X in reverse order and referring to two additional columns on X, okay? So what you would do is look at the right-hand side, find what it is, remove it, and replace it with what it has. And then you would reverse it, store it as two additional columns on X. And this is, you need to be careful that this is not 10, 11, 12, all the way to 20. This is just numbers 10 and 20. So you only have two numbers here. So this expression will be executed four times. So you have 0, 10, 0, 20, 5, 10, 5, 20. All right? And for each value of A and B, you need to calculate that expression and store it to the end of X. All right. There's a slide in one of the lecture notes that has more examples like this. So this smaller than or equal to sign, you cannot really, it doesn't really give you the semantics that you would hope for. This does not mean X is between -3 and 3. MATLAB will always perform operations one by one. So it will only consider a single operation and the two arguments. So it will perform this, replace it with its result, and then perform the next operation, replace it with its result. Okay? There's the operator precedence, where the rules for which operations to perform are listed. And that's how you solve this next problem, okay? Certain operations are performed before the others, depending on whether they are arithmetic, logical, or relational, okay? There are some functions that you need to know. So any, those are two important functions. XOR is also another logical operation that was covered in the slides. The programming problems are going to be very similar to what you have in the homeworks. They're not going to be any more difficult, and you will have access to, I lost my slides. You'll have access to your old homeworks, so you can make use of them to solve these homework problems, and you will have 4 hours total for the midterm, from 4 to 8. Okay? You don't have to use all of it. Any questions, comments? All right.
I have a question about the final. Are we going to be given 4 hours for the final?
I'm trying to arrange that.